Let us explore the methods for determining gravity centers. One of the methods we have already discussed is the analytical method and the calculation of centers of gravity using ternary, surface, or curvilinear integrals for the cases of a homogeneous volume, a homogeneous surface, or a homogeneous line. For simple shapes, the centers of gravity can be found as standardized values in the reference tables. Let us consider other methods. In particular, one of the methods is the symmetry method. In the case that a body has a symmetry plane, the center of gravity lies somewhere in that symmetry plane. If a body has a symmetry axis, then the center of gravity lies in the symmetry axis. If a body has two symmetry axes, then naturally, the center of gravity lies at the intersection of these axes. In the case of an arbitrary body, when we are unable to identify symmetry axes, we have to resort to an empirical method, for example, a method of suspension. This method is as follows. Let us consider a part to be suspended at two arbitrary points. Suspended at one of the points, we are to have a suspension line, which we are drawing on the part. Suspended at the second point, we are to have another suspension line, and the intersection of these lines results in the position of the center of gravity of a plane figure. Quite frequently, if a figure can be fragmented into simple volumes, surfaces, or lines, we use the fragmentation method. This method is as follows. Considering this object, we can identify some parallelepiped and 8 cylinders. In this case, providing a reference system and introducing the coordinates of the gravity center for the parallelepiped, and we know them very well. The center of gravity of a parallelepiped lies in the intersection of its diagonals. And considering the centers of gravity of the cylinders, and we know them quite well due to the symmetry, we can write down the coordinates of the center of gravity for the composite figure using the well-known volumes of the parallelepiped and cylinders, as well as the coordinates of the corresponding parts. A similar method of fragmentation is utilized in the case of a plane figure to be fragmented. In this case, we consider a position of the center of gravity of a vessel, which is determined as the sum of the centers of gravity of a rectangle, a trapezium, and a triangle. For the rectangle, the center of gravity is known to lie in the intersection of the diagonals. For the trapezium, the center of gravity is positioned in the center of the median line. And for the triangle, the center of gravity lies at the intersection of the medians. The equation to determine the center of gravity of the composite figure are presented in this slide. Here you see respectively the area of the rectangle, trapezium, and triangle with the corresponding coordinates, which we have analyzed in the previous slide. In the case that we have to deal with a figure which have sizes and two of the sizes can be neglected, thus fragmenting the figure in such a way that we know the positions of each of the fragments individually.
Таким образом, что мы знаем положение центров тяжести каждой части в отдельности.
We can also determine the coordinates of such composite figure using the fragmentation method. And the length of the corresponding part and the coordinates of the centers of gravity are all fragments of such figure. Another version of the fragmentation method is the method of negative areas or volumes. In this case, a quite complicated part can be represented as three triangles and two semidisks. And in order for us to determine the center of gravity of such figure, we can use the method described previously. And the cut-out areas which we see here will be included in the equation, yet with the negative signs.